with some of the parts which I could not finish earlier. And after completing this part, similar type of regression analysis, some extensions, etc., which we are doing. After completing this part, in the first half or first half an hour, 40 minutes, today ZH will cover geographically weighted regression. So today I'm starting with some extension of the framework which we have developed so far, and after that you will be also introduced with a new kind of model, new kind of regression model, which is known as geographically weighted regression framework. Sharing my screen. Is the screen visible?
Yes.
Okay. So far, we have constructed the models where, suppose we have these three districts or these three localities associated with each other. So far, if Y is the crime variable, we consider the framework crime of this red zone will be affected by crime of this blue zone as well as crime of this green zone. So if blue and green are the neighbors of red, in that case, crime of red will be affected by crime of blue and crime of green. So when we are talking about spatial lag model, by spatial lag, we introduced lag in terms of the dependent variable. So if crime is the dependent variable, this kind of construct we developed so far. We discussed about lag model, we discussed about error model, then we considered if we bring one other endogenous variable apart from the default endogenous Y variable. So we discussed a lot of issues. However, explicitly, we didn't do something where X is also affected by neighbor of X. So far, we concentrated only on Y will be affected by neighbors of Y. So for the outcome or the dependent variable, there is a lag in terms of space. Today, we are going to discuss not only for Y, suppose for X2, there is a cluster. For X2, there is a kind of neighborhood effect. Then what will be the structure of the regression model and how to estimate that kind of regression model? So look, we developed a model where crime depends on house valuation. So I have written another variable h of val. So for h of val 2, we are considering h of val of red will be affected by h of val of green and blue. In reality, this happens. So for a single variable which we are considering as dependent variable in our analysis, only that will have some network effect. However, the variables which are affecting that particular variable will not have any network effect in terms of their own interaction. Okay, so this is not the real scenario. Sometimes X will have this kind of interaction among X variables. Sometimes it will not have that kind of interaction. So today we are going to frame the regression equation if not only in terms of why there is spatial lag, but also in terms of a few or one or all X variables, there are this kind of network or network effect or interactions or spatial lag, whatever you want to say, you can spell the thing in that way. So if I consider for X2, there will be a lag. The regression equation can be rewritten as y is equal to rho wy. By this time, you are quite familiar with this lag term in terms of y plus x beta. We consider in a lag model, we consider y is equal to rho wy plus x beta plus error, uc. And if it is the error model too, that is instead of SAR, spatially autoregressive model, if we also bring the error part, error related interaction or interaction via the error channel, in that case we can extend the model to SARMA, and we write the model as y is equal to rho wy plus x beta plus lambda wu plus v. So you are also familiar with that kind of model, which we call SARMA model. Here we are bringing a new aspect. Here we are bringing this new concept. X is interrelated with neighbors X. So that is coming via these weight matrix X of a particular locality, the set of X, all the X's, few X's, one of the X's, everything is possible, is related to the set of X of the neighboring areas. So for the lag, we are introducing the weight matrix W. So X has been written as Wx to indicate the lag in terms of X. And there will be a coefficient. That coefficient has been indicated by this eta. So the model is quite longer now. Along with SARMA, there is an extra term, eta Wx. So now we need to learn, if we want to incorporate this kind of spatial interaction in terms of X2, or the network in terms of X variables too, how to estimate the model. So here we have to do the things in two steps. First, we will use geoda. And using geoda, we will create a set of new variables. The set of new variables are nothing but the weighted X variables, or X variables with this kind of spatial lag. So first we will create the set of X variables, new set of X variables, that is, which will be the extensions of the existing X. So if h of val is there, we have to create w underscore h of val, say. If income is there, we have to consider, if we want to bring this kind of network effect, or we want to check whether there is any kind of network effect in terms of X variable too, we have to create a new variable, which is w underscore inc, say. So first we have to look at the set of X variables which we have in our hand. Then we have to decide whether we will bring this kind of network effect or try to start checking the network effect in terms of all X variables or few X variables or one of the X variables. That will depend on your research motive, research question. And after that, we will, after creating these variables, after preparing our table, we will move to geoda space and we will run the regression. We will frame the regression equation and we will run the regression. Okay, so we will do the things using two steps. This kind of model, before starting this practical part, we should understand this particular structure has a name. This name is Durbin model. This kind of model we call Durbin model, following the name of Durbin. So in the first step, look how to do this thing. First, you have to load your DBF file and you have to load the weight. So these two things are common. Whenever you are doing something using geoda space, this will be the first step, loading the DBF file and loading the GAL file. Okay, so this part I didn't mention here. After doing this thing, we will consider table, and in the table, we will click on calculator. As we click on calculator, you will get this kind of window. We want to set lag for the x variables. So though there are different options, univariate, bivariate, spatial lag, rates, date or time, we will click on this spatial lag option. After that, we will consider add variables. If we click on add variable, this particular window will open in front of us. Then we have to give the name of the variable which we want to add. There is some limitation of how many letters it will be able to read. Okay, so 1, 2, 3, 4, 5, 6, here 6 to 7 letters it will be able to read, not more than that. So we need to give the name of the variable accordingly. Within 6 to 7 letters, we have to finish writing name of the variable. We will use the child waste data, child related information. So and there is one variable called C marriage, which is taking care of the aspect that whether the mother of the child faced child marriage or not. So for that child marriage variable, if I create the network effect, or I want to create the network effect or the spatial lag effect, I will naturally give the name something which is related to C marriage. You can give any name. However, remember, when you are doing econometric analysis, step by step, you are extending your understanding or level model building. In that case, you should give something which will match to your analysis. So if I want to add with respect to C marriage, if I want to incorporate lag in terms of C marriage, so C marriage or some letters from C marriage I'll bring, and since this is the lagged variable, I am putting W underscore here. You can give the name anyway. However, if you do the things in this way, your understanding will be better. Then there will be an option where you want to insert that variable. Insert before you can define. This option is not mandatory. This option, writing the name of the variable, is mandatory. However, where you will insert this variable, that is not mandatory. So if you don't put anything, in that case, it will arrange the variable name following its default mechanism. So once you write the name of the variable, which is mandatory, and define where you want to put the variable, in the next step, you have to click on add. As you click on add, this particular window will open in front of us. Okay, so this will carry the name of the variable, weight it will carry, and it already we marked that spatial lag variable we want to create, and that lag variable we want to create for C marriage. So this option also you need to provide. So then it will write a formula that this W underscore C marriage is, weight matrix name is child.gal. So weighted C marriage. So it is writing the formula. It will write the formula in its own. If you mention what kind of weight matrix you are using, which is the necessary step without which you will be not able to do anything, only in the beginning you have to do this, and then you specify the name of the variable, click on add in that case, and click on this C marriage option for which variable actually you want to create the lag. You will get this variable with this formula. Once you get the formula specified here, you will click on apply. So, and finally, you will click on close. So as you complete this business, actually a new variable will be created, and that will be stored in your table, in your data set, in your DBF file. Once you create this kind of lagged X variable, then you have to follow the usual regression frameworks, which we have already discussed in context of spatial econometrics. That is, you can run the lag model, you can run the error model, you can run SARMA, whatever you want, you can go for that. If along with these aspects you want to bring the aspect of endogeneity in terms of any X variable, you have to do the steps which we did in the last class. You need to fix the instrument and you need to use an instrument for your specified X variable. So all these steps will be common. Okay, so let's start doing these things, and I think your idea will be clearer. Any questions so far? Anybody, any question regarding the structure of the model? So would you please open your Geoda first? Please open your Geoda. And please load child.dbf. I already loaded and therefore I'm getting this bar. Is the bar visible to all of you? So please load the dbf file, child.dbf, and also from the tools, from the weight manager, load child.gal. These two steps are complete for everybody.
Yes, ma'am.
Others?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay, very good. Next, please click on table. Table. Okay. Now in table, there is an option calculator. Don't click on add variable because you want to write, you just not want to add any variable in our analysis which initially you didn't add. So don't do that. You have to regenerate a variable from the existing variable, adding weight matrix to this. So you need calculator. Calculator. Click on calculator. As we are clicking on calculator, we are getting this window. In this, please click on spatial lag. As you are clicking on spatial lag, you are getting the options like this. Weight is already there because the software understood the child.gal weight matrix it needs to utilize. Click on add variable. This window is opening. I want to define a lagged variable for child marriage for the time being. If I want to add one more variable, we have to follow the same process. Suppose I want to do it for log wealth. So I have to repeat the same process to create that variable as well. So I'm giving a name W underscore C marriage. I think it will not go beyond this. Let me check. Check, as I'm writing too many things, this add part is not working anymore. So I have to reduce the thing. I am keeping it up to W underscore CMARR. Then clicking, okay. I told, there is an option insert before. You can use that option. Otherwise, it is reflecting the first variable in the table. So click on this. Since you want to uh, add one weighted variable for C marriage, you can click on PCIAF, so that just after C marriage, you will get W underscore CMARR. So I'm clicking this, then clicking on add. Okay, so W underscore CMARR is reflected here. And here, the left-hand side of the formula, that is also ready. Now, this left-hand side formula will be generated using this weight matrix and the variable which I am specifying to the software, the C marriage variable. For the C marriage variable, actually, I am creating this lag. So now the formula is ready. Child, that means child.gal multiplied with the vector C marriage or the observations under C marriage. So once you complete this thing, you have to click on apply. And then you need to click on close. So now if you click on table and if you click on aggregate, I hope you will get the variable W underscore CMARR just after C marriage. So when you are looking at the aggregate set of variables, from where you can actually find out average, max, mean, sum, etc., etc. In the list, you are getting a new variable has been created, which is W underscore CMARR. Or you can click on this table and you can check whether the variable has been created or not. Just after C marriage, we are getting W underscore CMARR. So everything is ready. Click on save so that your data is saved. Then close Geoda. You can run regression from here. However, we are going to run regression from Geoda space. Okay, before moving to Geoda space, you can do the thing from here to regression. Here you will get the ML estimates. And from the Geoda space, you will get the 2SLS estimates, ML estimates, everything you will get. So if you click on this, your Y variable, you can consider P waste or PCIAF, whatever you want. PCIAF, this time we are considering. And then in the X variable, we are considering C marriage, W underscore C marriage, temperature, then PADO. If we want to bring wealth, you can incorporate wealth. If you don't want wealth today, keep it, you can keep it here too. Okay, so new thing is, along with the C marriage, we are bringing W underscore CMAR, which we generated from the existing set of variables. Okay, after doing this, click on wait file. click on spatial lag and run your regression. Your output is ready. This is your output. You are getting dependent variable. Whatever information you got earlier, you are getting that thing only because you are using the same software and using the same mechanism. So you are getting the result which is expected, So you are getting report for R square, Akaike information, sewage information, etc. Number of observations, degrees of freedom, everything you are getting from here. Okay, as we are moving to the coefficient wise table, we are finding, W health variable PCIAF, which is the default if you run the lag model. PCIAF is a function of PCIAF of the neighboring districts. So you are getting W underscore PCIAF, which you got earlier when you are running the lag model. This lag is significant at 1% level of significance. Then you are getting C marriage. You are also getting information regarding W underscore C marriage. We are finding this variable is insignificant. So given C marriage and other variables, we are not getting any network effect for the variable C marriage. PCIAF will be determined by C marriage, but not, W underscore C marriage. That is when we are considering, along with the C marriage, the lag of C marriage that is becoming insignificant in our analysis. Temperature and education, these are statistically significant. We are getting information or the regression diagnostics for Rush-Pagan test, which is checking heteroscedasticity. We are also getting test result, likelihood ratio test for the spatial lag for weight matrix child. And this spatial lag is statistically significant. That information we are also getting from this probability value of W underscore PCIAF. So that's the idea. Now here you are getting this kind of result. You can check another thing, instead of PCIAF, if we bring P West here, we are bringing P West, say, another variable, and run the same regression. Let's see what happens. I just changed the Y variable from PCIAF to P West, and C marriage, W underscore C map, temperature, education, we are keeping as it is. Weight has been clicked. Therefore, the weight matrix we have considered is here. And then suppose we are running the same spatial lag model. Click on run. So let's see what is happening now. W underscore P West is significant at 1% level of significance. C marriage and W underscore C marriage, both the variables are becoming insignificant. Okay, so they are playing certain roles when you are bringing this kind of network. In that case, in terms of child marriage variable, that is changing the structure. Initially, when we didn't consider any network effect in terms of C marriage, we always found C marriage to be statistically significant for the same variable P West. Now, this time, when we are bringing C marriage along with its lag, we are finding both the C marriage and the lagged C marriage, these things are becoming insignificant. The message I want to give you, In case of regression analysis, it is not that whatever you learned, you have to bring all the aspects in your analysis. And you should not feel that if your model is bit complicated, then only it will be, really, really accepted or wonderful. It will be, very good. So it is not like that. You have to select the right set of variables and the right model. If OLS is the best thing, you go for OLS. If really there is some spatial lag, then only you go for spatial lag. Okay, or there is spatial error, you go for spatial error. So by force, please don't try anything. Now, in this model, really there is the spatial aspect. It is not a spatially random model. Definitely, there is spatial aspect. However, the spatial aspect is important in terms of the y variable only when we are bringing spatial aspect in terms of one of the explanatory variables, child marriage. It is actually not working. You can check if you bring the interaction aspect for PA what is happening. You can try the thing on your own, or you can consider the temperature. Okay, if you find both in case of temperature and education, the lagged variables are working very good. In that case, you can plan for another model where you will keep C marriage, temp, then lagged temp, PA and then lagged PA and check whether you are getting a very good result or not. So you have to explore the things in this way and finalize your model.
Ma'am,
Yes.
ma'am, when I'm doing in Geoda, then it is working perfectly. But in Geoda space, it is showing that the weight file of the X variable contains some missing values. So there was some problem in working. So and I checked the DBF file of the aggregate. So it did
Because
contain
method
some.
is changing. Anandavita, method is changing. Here we are using maximum likelihood estimation technique. This is the default method estimation technique in Geoda. In Geoda space, when you are using 2SLS.
Yes, ma'am.
Okay. So that's the reason why you are getting some different result when you are using Geoda space. Clear?
Okay, ma'am. Yes, ma'am.
So this is also the thing, whether your ML will work better or GMM will work better. So all these things you need to explore. Okay, next you can click on spatial error and you can run the same regression. You are getting the result, and by this time you did all the things, several times. So I hope you will be able to analyze the model. So this time check when you are using the ML method and spatial error model, C marriage is becoming insignificant. However, W underscore C marriage, it is significant at 5% level of significance. Okay. Here we will be not able to do SARMA, and for that matter, for the regression part, we generally use the Geoda space. Okay, so I'm closing everything, closing this too, and I am opening Geoda space. Okay, so, bring your DBF file here, bring the GAL file here. Okay, consider Y variable. consider the set of x variables. Okay, so we are bringing these things, and then you can run the spatial lag model. GMM method has been selected. Run it. You are getting the result. Okay, so W underscore C marriage is significant at 10% level of significance. However, C marriage is not significant. This kind of result you got for spatial error model when you use the ML technique, maximum likelihood technique. So here too, you can use the ML technique and run the model. Okay, so C marriage is insignificant. W underscore C marriage is significant. So, both the both the ML as well as GMM are giving similar kind of result here. Okay, it's not that both C marriage and W underscore C marriage are insignificant. Here we are getting W underscore C marriage is significant with the p-value 0.09. Just significant at 10% level. If you consider 5% level of significance is the maximum, it is insignificant here too. Okay, I'm not estimating spatial error model, directly going to spatial lag plus error model. So let's run this thing. Okay, so we are getting this result. P waste is becoming insignificant.
Ma'am.
Yeah.
Ma'am, for all the three cases, when I'm trying to run, it's showing W's weighted C marriage has missing values and it's not running the regression.
Same, ma'am.
Yes, ma'am.
Yes, ma'am. It is for me also.
You didn't create the variable perfectly. Your formula was not right, or you didn't save the variable perfectly. Okay. So once again, I'll show you what are the steps you need to do. Okay. Okay, so I think you understood this part. You understood more or less this part, because we are doing the things which we did earlier. So we ran a SARMA and we are getting the result like this, Okay. So here there is certain problem while it tried to calculate some of the standard errors. Some of the standard errors it could not calculate, and for that reason, we are not getting the Z statistic as well as the probability value. So these are the examples. Actually, every model will not fit for every cases, So when we ran the SARMA, there was certain problems related to calculation of standard errors, and for that matter, we are not getting result for some of the standard errors. However, this is the mechanism by which we can incorporate lag for the x variables too. Okay, so I'm closing everything. I don't want to all these things. Okay, so since some of you could not, for everybody this is happening, or for some students you could do it perfectly?
Yes, ma'am. অনেকের জন্যই হচ্ছে।
রেজাল্ট পেয়েছো এরকম কেউ আছো নাকি সবাই পাওনি? Is there anyone who could do it? So everybody is facing a problem.
Yes, ma'am. Missing values.
Ma'am, actually, four rows are missing in WC marriage. When the data is saved, 4 rows are missing.
Yes, ma'am. They are missing values. Ma'am, Andaman Nicobar ওগুলো ম্যাম মিসিং ভ্যালুজ আসছে বলে ম্যাম আই থিঙ্ক করছে।
আচ্ছা, ঠিক আছে, ঠিক আছে।
ম্যাম জিওটাতে কিন্তু ছিল স্পেসে প্রবলেমটা হচ্ছে।
আচ্ছা আচ্ছা আচ্ছা, ওই ডাব্লিউ আন্ডারস্কোর ভেরিয়েবলটা পড়লেই ওটা দেখাচ্ছে যে তোমার ওটা মিসিং।
Ma'am, in actual table also it is missing. I checked it. Row 696, 701, the values are missing.
ওই কয়েকটা মিসিং হচ্ছে বলে ওরা বলছে প্রবলেম হচ্ছে। সি ম্যারেজ তো স্ট্রিং ভেরিয়েবল নয়। Okay, so I'm checking and doing the thing. Give me 1 minute. I'm again opening the thing and checking it. Let us check, the problem. Okay, so I'm loading the DBF file. And after that, tools, weight manager. Okay, so this part is done. Next, I am going to table, calculator, clicking on spatial lag, then clicking on add variable, giving a name. Achha, this time, before doing so, I'm sorry, I have to drop that variable. So take table, delete variable, and please drop the earlier created variable. This W underscore C M A double R, delete. Okay, close it, save it. So it has been deleted. Next, table, calculator, click on spatial lag as we did first time. Click on add variable, give the name. Suppose this is the name we are giving, WCMARR. We also clicked on insert before. So insert before PCIAF. Click on add. So this variable has been added. Then we have to click on for which variable actually we need to create this lag. So click on C marriage. So formula has been written. Click on apply. Close it, save the data. Open the table, click and check whether this variable is here. Now you are telling that there is some missing variables. Yes, 703 data we found while we ran the regression.
701.
Yeah, yeah. So there are 1, 2, 3,
এগুলো হচ্ছে
আইল্যান্ডের জন্য, হ্যাঁ, আন্দামান নিকোবর, ইয়া। সো 1, 2, 3, 4 ভেরিয়েবলস, সেটা ওরা বলেও দিয়েছে, অনেকেই বুঝেও গেছে। সো 4 missing values are there. Okay, yes, 4 missing values are there. Actually, what you can drop the 701, etc., for which there are missing values. However, since I could do it for Geoda and Geoda space, once again I need to check which problem you are telling is coming. So once you do these things, close it, because you didn't face the problem with Geoda, you face the problem with Geoda space. So I'm closing this. And I am opening Geoda space. DBF file, weight file, Y variable, so now are you getting, those who are facing the problem, the missing variable, etc., are you getting the variable now?
No, ma'am. Still the is rewarding motivation.
Don't worry, we'll see later on.
Yeah, because
we'll have to look at your screen and then find
Yeah.
out.
like the last time. Okay, so some other people, Ognija could not do it. Other people?
Same, ma'am. No, ma'am. Couldn't do it.
So nobody is getting this thing, or some people are getting this thing. Foram, Anindita, Urpita, are you getting
No,
this
ma'am.
thing?
The same error is coming.
Yes. Same as
নিচে গিয়ে দেখে নাও তো, নিচে বা একদম উপরে দেখো তো ভেরিয়েবলটা আছে কিনা।
হ্যাঁ স্যার আছে, কিন্তু মিসিং ভ্যালুজ বলছে।
না, মিসিং ভ্যালু তো বলবেই, বিকজ সি অ্যান আইল্যান্ড অ্যান্ড আইসোলেট, এর তো কোনো এর ওয়েটটা কি হবে, নেবার্স তো কিছু নেই। স্পেটিয়ালি ল্যাগ মানে কি,
Spatial,
তোমার একটা চাইল্ড ম্যারেজ আছে তোমার রিজনে, তোমার নেবারদের যে চাইল্ড ম্যারেজটা। নাও ইফ ইউ আর অ্যান
Yes.
আইসোলেট, you can't have any.
this kind of thing is required, otherwise you will not get it. But তার জন্য you will be not able to run anything. This I am finding problem.
ও রান করতে পারছে না, সেটা ইজি, সেটা আমি সলভ করে দেবো।
তোমরা রান করতে পারছো না, না তোমরা এখানে ভেরিয়েবল লিস্টে ইনকারপোরেট
রান হচ্ছে না।
না ম্যাম, রানই হচ্ছে না।
রান হচ্ছে না, ওখানে
Run
বলছে
হচ্ছে
মিসিং
না।
ভ্যালুজ আছে ভেরিয়েবলে।
একটু দেখে নাও।
ম্যাম জিওরাতে রান হচ্ছে, কিন্তু স্পেসে রান হচ্ছে না।
হ্যাঁ ঠিক আছে, আমি বলে দিচ্ছি, ওটা ইজি। 1 মিনিট আমাকে একটু দেখে নিতে দাও কোনখানে করতে হবে। হ্যাঁ, তোমরা যেটা করো, তোমরা এই দেখো এখানে যে সেটিংসটা আছে, শো অ্যাডভান্স সেটিংস, এই যে গিয়ারের মতো যে আইকনটা, ক্যান ইউ সি দিস আইকন?
Yes sir, yes sir.
Yes.
Yes, sir.
The last option is other. I'm clicking on it. So you have to, I mean, those who cannot estimate it, will see that this is the screen that you get. Just click on this, replace missing values with 0. And then click on save. Then see whether you can run it.
হ্যাঁ স্যার এবার
Yes,
হয়েছে
sir. Now it's happening.
Okay. So you can run this model in two ways. One is you drop the isolates,
Yeah.
and the other is you just replace the missing values. Because if you have isolates, Geoda space will not run. Any spatial regression will not run.
Okay, is it all right now? Everybody could do
Yes.
it?
Yes.
Yes, ma'am.
Okay, very good. Okay, so more or less things are done. The Durbin model, I hope you understood. Now you explore, you do the same in terms of other explanatory variables, and please check what you are getting. Okay, finally, I'd like to add briefly, a few points. Okay. That is related to what is the difference basically we are finding between a standard regression model and the spatial regression model. As you are understanding, these are the extensions of OLS, 2SLS, maximum likelihood. We are around the known aspects, we are already familiar with this kind of estimation technique. We are using these estimation techniques and trying to tell a new story. In context of regression diagnostics too, we are doing the same. We are familiar with the JB test, the heteroscedasticity related tests, etc. And those aspects we are bringing here and trying to tell the story regarding the regression diagnostics. One new thing we did here, which was not there in any regression diagnostic analysis previously, that is the Moran-Psi, then global Moran, local Moran, Lisa. This spatial autocorrelation story is totally new. Therefore, here we start with that spatial autocorrelation, because this is something new which was not there in any kind of standard analysis. So in the light of the entire thing, what I like to add, the assessment of the quality of spatial models has slightly different rules than the assessment of other types of econometric models. First of all, the normality or typical heteroscedasticity discussion of the residuals is not generally studied that much in context of spatial econometrics, because spatial models do not have such assumptions that error should follow the normal distribution. Here we are allowing heteroscedasticity, space-wise variability, etc. will change. This is the default assumption here. Space is playing an important role here. So there will be no heteroscedasticity at all, etc. These things are not coming that much in context of spatial analysis. Every error should follow normal distribution. That is not required here. Second, which is very, very important, in a general model, if there is any outlier, if any outlier is detected, we have to remove that outlier from our data set, because all the analysis which we do in general are mean-centric approach, and mean will be very much affected if there is any extreme value. So we are in fear in the standard regression analysis if there is any outlier. However, in case of spatial analysis, you don't need to remove any outlier. In fact, their removal could cause spatial discontinuity and data deficiencies in the areas on the related map, and therefore an incompatible spatial weight matrix you will generate. So what I want to tell you, you are already familiar with the box map, which is identifying the outliers. So outlier is one district or one household or several districts or several households. So if you drop those things from your map, maybe some neighboring areas will become isolates. So we don't need to drop any kind of outlier from the spatial analysis. Don't go for dropping any kind of information, any kind of data or outlier from the spatial analysis, because that can make your set, disjoint from the rest of the part. Third, an important element of diagnostics in assessment of spatial autocorrelation of residuals using modern size statistic is very, very important here. So this kind of statistic we don't use in context of standard regression analysis. This is new. This is, playing a major role in context of spatial analysis. So we should be very, very careful about this. Finally, in standard regression analysis, while we try to assess goodness of fit, our focus is on multiple R squared, adjusted multiple R squared, etc. Here, since we are using the maximum likelihood estimation technique simultaneously, so whenever you are estimating the standard regression model using the ordinary least square technique, then too, you are finding the report of Okaiki information criterion, Bayesian criterion, etc. So while you will explain or analyze your goodness of fit, not only report R square or adjusted R square type of information, but also always report Okaiki information, Bayesian information, etc. So these are the few things please keep in your mind when you are going to analyze this kind of spatial models. For the rest, you start practicing these matters, whenever you will find any difficulties, please report. We will like to take care of the issues. Now, I'll hand over to Z8 sir. Zakir will tell you the story related to geographically weighted model. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Welcome.
Yeah, just give me some time so that I can load my tea. পরে কেউ জয়েন করে So can you see my bright new slides?
No, sir.
Okay. এত কষ্ট করে করলাম, তোমরা দেখতে পাচ্ছ না?
Yes, now we can see.
Very good. So actually there are 3-4 extensions of the spatial regression models. I'll discuss about some of them later on in the last class. But today I want to discuss one important extension. Unfortunately, this is an extension which cannot be covered using either Geoda or Geoda Space. I'll discuss the software packages which can do it later on. But So this will be basically a theoretical lecture, although I'll show you some results of what type of output you're going to get. See, so far the analysis that we have carried out conceives space as an isotropic phenomenon. In other words, we are looking at the relation between two variables, which is the dependent variable, and an explanatory variable, x. The basic assumption is that the relationship is same in all points of the space. So if we estimate a regression model, the relation between y and x is given by the coefficient beta. The spatial regression assumes that beta is stable throughout over the region. So in other words, let me see over here. So let us say we have three regions, some regions over here, and when we estimate the regression takes the form like this. And we also have, this is the spatial lag, and then we have the moving average. This is the error part. So in other words, if I want to look at the relation between y and x1, it is given by beta 1 over here. It is beta 1 here. It is beta 1. It is beta 1 everywhere. So in all the regions, so if let us say that I'm increasing x1 by 1 units, how much will y go up? It will go up by beta 1 in all the different regions. If I increase x2 by 1 unit, the impact on y is given by beta 2, which is same in all the units. This is called the assumption of just one second. Yeah. Basically, what we are trying to say is the parameters are stable in all regions. The parameters do not vary. But the advantage of this method is the calculations are simplified. The model becomes very simple. Estimation is also very simple. But when we are looking at spatial phenomenon, see, the basic assumption is that location matters. And one way in which location matters is the coefficient 2 can vary. For instance, let us suppose we are looking at the impact of global warming on child malnutrition. Let us say that temperature increases by 0.1 degree. Will the effect be what will be the effect if temperature rises in Darjeeling by 1 degree? And if it rises in Rajasthan, which is already very hot, by 1 degree? It will be very unrealistic if we assume that global warming has the same effect in Darjeeling and Rajasthan. The environment is different in both the states, and therefore any further increase in the temperature is going to have different effects depending on the initial situation. Now, if we incorporate this into our regression model, what it means is the parameter values, beta 1, beta 2. What is the value of beta 1? It depends upon the observation or location. Or more specifically, the basic assumption is that we have clusters. So there are some, in the cluster, we have some districts or wards or whatever, or points, which are lying close to each other. And beta is more or less same in this cluster. If I move to another cluster, within the cluster, the value of beta will be more or less same, but between the first and second cluster, there's going to be a difference. For instance, take the case of a housing market. These types of models were first proposed when we wanted to look at housing, the price of houses. So the impact of a variable on housing price depends upon on the location of the property, whether the property is located in a center or in the suburbs. So suppose you have a multi-storied building and you're on the top floor. Now, if your building is in the center of the city and you're living on the top and there's a flat on the top floor, it means that you suffer from less pollution, air pollution, sound pollution is much less, and you can also have a very nice view. So an apartment located at the top will have a very high price. On the other hand, if you go to the suburbs, the transport is much less, pollution levels are much less. So it is now the flats which are at the lower levels that are more costly. People will prefer to live in the bottom floors. Underground parking, well, if it's a very dense building, very closed, you're competing for space. Underground parking is a huge disadvantage. So if you're living in the city center, if the flat is in the city center, where there's a lack of space, competition for space, underground parking means that the value of the flat is going to go up. On the other hand, if you move to the suburbs where you have a lot of space, people would prefer to have on the ground parking. So basically, the assumption that the coefficients vary across regions is based on the assumption or belief that in a space you have a cluster, you have homogeneous clusters. Within a cluster, the model coefficients are constant, but each cluster has differences. As a result, when you move from one cluster to another, the coefficient is going to change. Now, the heterogeneity of this heterogeneity, that clusters are different. And so the relation between X and Y varies between clusters, can be modeled in different ways. And GWR is not the only way of doing so. Each of these approaches makes a common assumption. The assumption is that if you have clusters in your data, then the variance is, and within the clusters, the variance is small, then the parameters of the model will be stable within the cluster. So this is the assumption which is common in all the approaches. I hope you can see them. So this is a chessboard pattern which we have taken, and the assumption is that everything is the same. Now look at this. So over here we have several clusters which are colored in different ways. You have a yellow cluster, you have a green cluster, you have a blue cluster. And the basic assumption is that over here, the variance is low. Okay, so if I compare between a yellow and blue, the variance is high. And this implies that you have parameter instability. The parameter of beta is going to change. But if you compare between, let us say, two yellows, the variance is low and beta is going to be more or less same between this region and this region. Now, as I said, that there are several approaches which can incorporate this feature into spatial regression models, but the most popular is the geographically weighted regression, what we call GWR in short. The advantage of this model is it's very flexible. So even if the clusters are very small, this model can be estimated. We don't have to formulate the clusters ourselves. The model itself does it for us. And third, it is very simple. We assume a linear function so that interpreting the coefficients becomes very easy. The foundation is of GWR is in the what we call the local regression model. This local regression model was adopted in spatial econometrics in 1996 by Brunson, Fotheringham, and Charlton. What it says is, the local regression model says that the value at a given point depends upon its surroundings, the nearest neighbors. So if I'm taking the value of, let us say the value of, let us suppose we are taking per capita income. So if I'm taking per capita income in Calcutta, the surrounding areas is going to determine the per capita income in Calcutta. In the classical approach, how do we know neighbors, etc.? It depends upon, it's based on the explanatory variables, X matrix. So that means if I take two regions, no, I won't take this. Let us say I've got two regions, R1 and R2. So the value of Y is, let us say 100. We have got some values of Y over here. The value of Y is not important. X1 is, let us say 100. Here also it is 105, but here it is 70. So in the local regression, we assume that if I look at X, okay, for this region, region 1, which is closest to 100, the value of R2. So that means the value of X over here is going to affect the value of Y in region 1. So Y1 will be affected by, of course, X1, but it is also going to be affected by X2. On the other hand, suppose I'm taking a different case. So this is Y1, this is 100, R2 is, let us say 200, R3 is 95. In this case, Y1 depends upon X1, the standard regression. But now, who is closest to R1? R3. So it is X3 which determines Y1. So in other words, how do we determine who is a neighbor? By looking at the value of the X, the explanatory variable. Is this clear, everyone? In GWR, we follow the same approach, but now Okay. 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 So in a local regression, the value of y, so we are looking at a region I. So the value of y in a particular region I is a function of, depends upon, let us suppose I've got only one explanatory variable. So it is obviously going to depend upon xi. In addition, it will depend upon the value of x in the neighboring regions. Now, what do we mean by neighbors? A neighbor is defined as any region whose x is close to xi. So it is not geographical neighborhood. So for instance, let us suppose that we have a region like this. And this one. So the value of x is 100 over here. It is, let us say, 10 over here, 9 over here, 7 over here. And over here, it is 95. Okay, so I've drawn 4 regions over here. Which of them is the neighbor? We don't look at geographical contiguity. If I'm looking at geographical contiguity, then these should be the neighbors. These should be the neighbors. Now, what I'm doing is I'm looking at the value of x. So over here, I can see that this is 100, this is 95, very close to, the values of x is very close to each other. So I'm defining neighborhood in terms of similar values of x, not in terms of geographical contiguity. Is this clear, Moyuk?
Yes, I got it. Thank you.
So this is what we do in local regression models. When we apply this, when Fotheringham applied this to spatial econometrics, instead of defining neighborhood in terms of similar values of x, he looked at the distance. So in other words, we are going back to the geographical contiguity. Who is a neighbor? Points which are close to the original point. So who is the neighbor of I? Out of the 706 districts, neighbors are those who are close to I. So typically the GWR model is written as, so over here, okay, it's written as beta 0, and you can see within brackets, there's a UI, VI. These are not the error terms. Summation Px K1. Okay, so if we have 2 explanatory variables, the regression will be like this. If I have 3, beta 3 will be added. So I is obviously the observation. So I is the different districts. So I'm discussing it in terms of the child marriage data. So I denotes the district. Y is obviously the percentage of stunting. So YI is the stunting in a particular district. And X is sorry, এটা K নয়, এখানে we'll have I over here. X1I. So this is the first explanatory variable. So X1I will be child marriage in district I. X2I will be, let us say, night lights in district I. Okay. Now, what is UIVI? These are not the error terms. They are the geographical coordinates, the latitudes and longitudes. So now what we are saying is the value of beta 1 is going to depend upon the geographical coordinates. Now, what happens is we go to, if we look at the model, so all these are regions. So we have the centroids. So GWR doesn't work for polygon data. You have to convert the polygon data into point data. That's not very difficult to do. You can just create the centroids. You know how to do it. Just open the themeless map, right click, and you will see an option, add centroids to tables. So you have the centroids at that point, and the centroid is given by the coordinates. So it is U1, V2, this is U2, V2, this is U3, V3. Now, what we are saying is Y depends upon, this is the first coefficient. It depends upon UI and VI. Okay. So when I'm looking at region 1, I have a particular coordinate. So it is going to take beta 1 will depend upon U1, V1. Beta 2 will depend upon, sorry, this should have been I. It depends upon U1, V1. So this is for region 1. In region 2, it is like this. Beta 1 and beta 2 depends upon the latitude and longitude of the centroid. And because it changes, this beta 1 and this beta 1 are different. This beta 2 and this beta 2 are different. So in other words, what we are saying is this will be beta 1, 1 and this is beta 1, 2. Okay. Here we have beta 2, 1 and beta 2, 2. This is beta 3, 1, beta 3, 2. So the coefficient vector is different for each of the regions. Is this clear? So if I have got 7 in the district marriage, in the stunting data, we had 707 districts. For each variable, we are going to have 707 coefficients. If I have take 4 explanatory variables, I will have how many coefficients? 707 into 4. If I'm taking 6 explanatory variables, 707 into 6 coefficients. Is it clear? So that means every district or region will have a separate regression, and the coefficients are going to be unique for that particular region. So when you move to another region, the coefficients are going to change. So as I said, if I've got 707 districts, if I estimate the GWR model, I'm going to have 707 regression models. GWR has been applied, was initially applied to study property valuation, but it has been applied to other domains, epidemiology, famine in Ireland. It has been used to study crime. And one of the PhD scholars in our department also published a paper in Journal of Interpersonal Violence, Richa Kothari, in 2022. So far as estimation of these GWR is concerned, ArcGIS, a very expensive package, can estimate this. I have used, Richa also used GWR, which is a menu-driven package which can be used very easily. It's pretty similar to the Geoda. The only thing is you have to take the DBF package and convert it to a CSV, comma delimited package. You can do it very easily. You just open DBF in Excel, you know how to do it, and you just click on Save As. And in file type, you change the file type from DBF to, well, you won't get DBF, but change it to CSV. So CSV files are read by GWR, and you can estimate the GWR model. GWR is developed by those who formulated this GWR package, so it's pretty good. The problem with GWR is that it was formulated in 2013. And if you try to install it in the current Windows version, sometimes you get a problem. It will say that this DLL package is missing and it may not work. R has some packages, SPGWR, GWRR, Spatial, and the GW model is the best out of all these 4. But R is pretty difficult to learn. You can also use SpaceStat, which is free. You can use it for at least 1 year. So if you download SpaceStat, which was developed by Luke Anseling, the same person who developed Geoda and Geoda Space, they will give you a 7-day note period. 7 days or 14 days, I don't remember. If you apply, they will extend it to 1 year. What happens after 1 year, I don't know. I'll just show you, since we are not using R in this course, I'll show you the outputs and how to interpret them. So the first step in GWR is to estimate the OLS. And over here, you can see that we have taken 4 regression coefficients, X1, x2, x3, x4. So y is a function of 4 variables. And the OLS results, the coefficients are intercept beta 0 is 79, beta 1 is 47, x2, x3 are pretty low. And you can see that if you look at the t values, the intercept is statistically significant. So is x1, x2 at 5% level, at 10% level, x1 and x2 are significant at 5% level, and x2 is significant at 5% level, at 10% level. Okay. Before coming to GWR, we have to locate GWR, all the observations in space. Generally, as I've said before, we use the concept of centroids to define geographical locations. So if you have point data, each point is automatically defined in terms of coordinates. But if you have polygon data, you have to convert it to point data. Geoda allows you to do it. Then you have to define. So over here, you can't really go for a contiguity, Queen's neighborhood, Queen's matrix, or Rook. You can't use those methods because you're using point data. You have to use a distance-based approach. So what is the optimal distance? Remember, in distance-based approach, we define neighborhood in this way, that we defined a critical level D star, and if Di is less than D star, Ij is less than D star, I and J are neighbors. But if Dij, the distance between 2 points, Dij, I and J is greater than D star, then I and J are not neighbors. In GWR, this critical distance D star is called bandwidth. And you have to basically use, well, I'll discuss how to determine the bandwidth, because obviously that becomes very important. But then we have to we use a kernel weighting function for determining the weight. And of course, we have to incorporate the Tobler's law. So which means that there has to, the kernel function has to embody the distance decay. So if you have got, you're taking 2 points, x1 and x2, and they are pretty close, you give it greater weightage. But if x1 and x3 are far away, then you assign less weightage to it. Now, kernel is something that, function is something that you don't know. Okay. Before coming to that, there are 2 ways of defining bandwidth. One is using a fixed bandwidth. So in case of every location, we use the same bandwidth. D star is same for all locations. So what it means is that if you take points located in a very dense cluster, so you have points like this, and this is your region. Okay. So you can see that you have a large number of neighbors. On the other hand, suppose this is your main point, and let us suppose your points are dispersed. So if you take the same bandwidth, sorry, it's not very well drawn, you can see that you have only one neighbor. So neighbors, the number of neighbors goes down in less dense areas. So over here, this diameter, this D star, this is a constant. That is why we call it a fixed spatial kernel. In case of adaptive, what we do is, if you have a large, if you have a very dispersed settlement, you take a large diameter. So in other words, if it is dispersed, D is large, and if it is concentrated, D goes down. D is small. So over here, for instance, we will use a small diameter, this one, not this one. Here, we take a larger diameter. What will be the size? Well, the objective is to ensure that we have the same percentage of neighbors. So going back to the district levels, suppose over here we have 2 neighbors. So that means 2 out of 707. Here we choose the diameter such that we still have the ratio is the same. Is this clear? So once we use the bandwidth to determine the same number of neighbors in the adaptive, and in case of fixed, the number of neighbors is going to vary. So what we do is we take a point, we identify the neighbors, and we run a regression for only this subsample. So I've got a point over here, and these are the neighbors. And the blue ones, they are not neighbors. They are too far away, so we don't consider them to be neighbors. So what we do is, we take the bandwidth. These 4 are considered to be neighbors. So the sample size is 5. And we run a regression on these 5 variables. We then take another value. So now let us say we take this one. We again form a kernel, we again form a bandwidth. We find out how many neighbors are there. And then we run another regression over here for this. So in this way, we run, we estimate regression run coefficients, we estimate regression models for each of these observations. So generally the problem is, which one should you use? Fixed spatial kernel or adaptive spatial kernel? See, if your distribution is even, fairly even, you can go for fixed. But in space, you generally have clusters, dense distributions on one side, sparse distribution on others. So in such cases, you should go for adaptive spatial kernels. Now, how do we select the bandwidth? See, the bandwidth is treated as a hyperparameter. It has to be first determined. It is one of the variables in the model. If you take a different value of the bandwidth, all the results are going to change. Unfortunately, there's no theory by which we can determine the bandwidth. But what we can do is, there are various different types of error matrix. Default is cross-validation. Those of you who know lasso, you may recall the cross-validation. So we take the leave one out cross-validation. So this is basically the root mean square error. We drop the observation. So if we are running it for Calcutta, for suppose, we drop Calcutta and we find out the root mean square error. So in this way, we find out. So this is called the LOOCV, leave one out cross-validation. Among other criteria are the mean square prediction error, mean square prediction, mean root of mean square prediction error, RMSE, or even the Akaike information criteria. So now I've been referring to kernel function. What does a kernel function do? See, look at this distribution. Okay, so can we divide them into two clusters? This is very easy. Right. The blues are on one side, the reds on another. So we can apply, we can divide, or we can classify the distribution into two groups very easily. But look over here. So we have blue points and we have red points. The problem is how to draw a line in such a way that the blue and red points are distributed. So we have to use a linear classification method. The problem is it's not going to work over here. In kernel, what we do is we use a linear classifier to solve a nonlinear problem. This is converted to, this is in 2-dimension space. We convert it into a 3-dimension space. We bring in a 3rd dimension, and now we can see that the blue line, instead of using a line, we can use a plane to divide the blue lines, the blue points, and the red points in two different clusters. So over here, it's a 2-dimension. We have to convert it to 3. If you have a 3-dimension point, you have to go for 4-dimension, higher dimensions, and go for hyperplanes. Okay. Now, if we come back to selection of the, optimal bandwidth, we have different types of criteria. What GWR or any of the packages do is they use the golden search criteria, which was formulated by Greg. So what happens is you estimate a model and you get the, let's say, the Akaike criteria, or you get the leave one out cross-validation. Over here, we are using the cross-validation. So what we do is we go for large intervals. So we take a point and we make a very big jump. So we move from, let us say, 38, and then there's a huge jump, and we find it is 76. Then we try to gradually reduce the error. So we reduce the grids. Okay. So it is something like so I'm taking a jump up from here to here. So I'm taking a jump from here to here, and I see that, look, Akaike is, you know that we minimize the Akaike information criteria. So as we move from here to here, the Akaike goes down. So we take a larger interval. the Akaiki is still falling. So we take this, and now the Akaiki is rising. So then what we do is we focus on this segment. Okay. So I click on here. So I compare between these 2 points. What happens over here? Then I narrow it down still further. Okay, so I'm reducing the size of the grids. These are called grids. And in this way, I'm gradually coming closer and closer. And this enables me to find out at what point the Akaiki criteria or whatever criteria I'm choosing is minimized. So you can see that we have gone to a very close band. And when we have reduced it, we really have to go for very fine changes. And once we find that, look over here, the RMSE, the LWCV is not, the cross-validation error is not changing. See, over here, the cross-validation error is changing. But from here onwards, the cross-validation error is same, 11.15939. So that means we are going to stop over here. We have found out the optimal bandwidth. The good thing is you don't have to look into all these. The package will find out, will do all this for you, and it will identify what is the optimal bandwidth. Once you have found out the optimal bandwidth, the package will estimate the models. And remember that you no longer have one set of coefficients. You don't have a vector like this. We have got 3 variables. We have got 4 variables. So in OLS, we get one vector. If we estimate a spatial model, we are still going to get a vector, a single vector. So whether we are estimating OLS or whether we are estimating the SARMA model, we get just one coefficient vector. But when we are going for GWR, depending on your districts, so for each districts, you are going to get different coefficient vector. So we get one coefficient vector over here. This is a separate vector for region 2. Okay. So we have got 707. So we are going to get, well, actually, there are 4 isolates. So we will get 703 coefficient vectors. Well, reporting that is impossible. So what the package will do is give the descriptive statistics about the coefficients. So you can see that this part is the minimum of the coefficients. So these are x1, x2, x3, x4. This is the intercept. This is the first quartile. This is median. This is the third quartile. And this is the maximum. And the global is the OLS coefficients. Okay, is it clear, everyone?
Yes, sir.
We have got 703 coefficients. What we can, the general practice is to map them, map the coefficients. So this is for x1 and x. Okay, actually both are for x1. The left-hand side, they have plotted the coefficients. And the right-hand side, they have plotted the standard errors of the coefficient. So what the GWR is, it will give you the coefficient value in a particular district, the standard error of this coefficient, and the confidence limits and the t values. So over here, they have plotted the standard errors. On the left-hand side, it is the coefficient values. So this is beta, and this is the standard error of beta. So we can see that beta is very important, has a very high value in this area. It has a very low value in these two clusters. Okay, so you can now understand hopefully what it means by the cluster assumption that I referred to earlier. Within a cluster, the coefficient is not varying that much. So within this deep pink cluster, coefficients are changing but marginal. If I go to this second cluster, the coefficients are varying from 85.01 to 85.11. Okay, so it's more or less same in these regions. Blue region 84.87 to 85.01. So there's not much variation across within this cluster. But if we compare between clusters, deep blue, light pink, deep pink, the coefficient values are changing. The mean of the coefficients will change. Now we have some diagnostics. The first diagnostic is that, well, it's a very complex model to estimate. And the first question is it really worthwhile to estimate this? Estimate this GWR. And the second question is that whether the variance, so the changes in the coefficients between regions or points, is it statistically significant or not? So Leung, May, and Zhang had written a paper in which they discuss certain statistical tests to answer both the questions. The first question, that is it worthwhile, which model should we choose, OLS or GWR? That is given by an F test of goodness of fit. So RSS 0 is your OLS and RSS G is the GWR model. So V1 is the parameters, N minus P minus 1 is the degrees of freedom in the OLS model. So this part. So N is obviously the sample size. P is the number of parameters. So in the model that we had discussed, we had 5 parameters, and so the degrees of freedom will be this one. V1 is the degrees of freedom in the GWR model, and that is more difficult, and I'm not discussing that. You can see the output, and the null hypothesis is that the models are not significantly different. In other words, there's no point in going for the GWR. OLS will give you the same results. The alternative hypothesis is GWR is better. And you can see over here that if F is very low, then we accept the null hypothesis. And over here, the value of F is pretty low, 0.98, which means that there's no point in going into the trouble to estimate the GWR model. The OLS is sufficiently fine. The second point is that other parameters vary versus the parameters are constant. So this is more or less a test for the individual coefficients. But previous one was for the model, whether we should go for OLS or whether we should go for GWR. Here we are saying that, look, let us take X1. It's quite possible that X1 is varying, but X2 is constant. And again, over here, what we see is that if you have a large F, as over here, we should go for the, we should reject the null hypothesis. So that means, in this case, for the intercept and for x1 and x2, the null hypothesis is rejected. So in other words, the coefficients are changing across regions. So what it means is the model will be a semi-parametric model. Beta 0 will depend upon your parameters. Beta 1 will depend upon the location. So will beta 2. However, beta 3 will be constant. This is the correct form of the model. So this is in comparison to a GWR, which is a non-parametric model, this is semi-parametric. Some of the coefficients are varying, some of the coefficients are constant. Okay. Sorry, আমি একদম ভুল লিখেছি আমি it should be the true form of the model is like this. So x3, x4 are going to vary. There's another test of parameter stability, whether the coefficient is varying or not. This is based on, this was suggested by Fotheringham. And this is the test which was used in the GWR package originally. I'm not very sure whether it still gives package. I think it does. So this is again a test of the individual coefficients. And the problem is the results you can see are the same over here, x3 and x4. Varies, but x1, x2 and the intercept is constant. No, sorry, এখানে তো critical level. These are the p-values, sorry. So this is the p-values. So over here, unfortunately, what we get is that in all cases, we have parameter instability. The coefficients are changing across the parameters. So the problem with these models are that depending on the test that you do, your results may change. In fact, not even over here, even this F test over here, whether OLS and GWR is better, there are some other tests. It's called the F2 test. And it can provide you with completely different results. Now, when we estimate regression models coefficients, we look at beta, but we also test for the significance of the beta coefficients. So we look at the value of t and we say that, look, the hypothesis that beta 1 is equal to 0 is accepted or rejected. Unfortunately, in GWR, it is not possible to test for the significance of GWR coefficients. We do obtain pseudo-statistic t, but this t value should not be used to test the hypothesis that a particular beta is significant or not. Okay. So globally, we cannot test whether the coefficients are significant or not. We can only test it for a particular region. So Fotheringham and Bine in a paper by Bine, they have given a procedure, but it fails. It does not really looks into the statistical properties and reliability of the testing method. So econometricians have argued that a t-statistics should be used only for exploratory data analysis. So in other words, we have plotted beta, we can also plot t. That is all. We can't do anything else. Okay, so I'll stop at this point. I'm sorry that I cannot show you how to estimate the GWR regression models, but you can try for either this SpaceStat, you can download it and see, or if you're good in R, you can also try the GW model package and see. But if you have any problem, you can always approach us and we'll be glad to help you out. Okay, so I've exceeded the time. I'm sorry to keep you so late. I'll end at this point unless you have some questions.